Section 4.1, Continuity. Now that we learned some basics about topological spaces, and now that we've learned how to build new ones out of old ones by taking subspaces or products or quotients, now we want to consider the relationships between different topological spaces. And for that we need functions. So let's look at definition 4.2. Let x and y be topological spaces. A function f from x to y is continuous if f inverse of v is open in x for every open set v in y. Okay. So the requirement is that if you take any open set v in your target here, and you look at its preimage in x, that has to be open too. Alright, so let's try exercise 4.6. Let x and y be topological spaces, and let x times y be the corresponding product space. Define the two projection functions p sub x, which maps to the space x, and p sub y, which maps to the space y, by, well, p sub x applied to a point in the product is just going to keep the first coordinate, and p sub y is just going to keep the second coordinate. Okay. Prove that these two projection functions are continuous, and remember we're using the product topology on x times y. Okay, well I've illustrated one specific instance of this, of these projection maps. So if you let x be some line segment and y be some circle, then x times y would be a cylinder, right? Because you can specify a point on the cylinder by sort of saying where it is on the line segment and where it is on the circle. And so that's one example. We want to prove the fact up here, not just for this example, but in general. So let's see how we can do that. Well, to show that p sub x is continuous, right, remember we have to take some open set in the target x and prove that its preimage is open in x times y. Okay. So let U be an open subset of x. Then we got to show its preimage is open, so let's see what its preimage is. The preimage of U under p sub x. Well, by definition, that's the set of all points x, y in the target, x times y, such that, well, p sub x of this point should be in U, right? But p sub x of this point is just x, so the requirement here is that x has to be in U. But what is that set? The set of all x, y, and x times y, where x is in U. That's just the definition of the set U times y, right? Because the first coordinate has to be in U, and the second coordinate can be anything in y. Okay, well I want that to be open, but it is, right? That's not just open, it's a basis element for the product topology on x times y. Hence is open. Right? This is base element because U is open in x and y is open in y, and that's how you get basis elements for the product topology. So we've shown that p sub x is continuous. We took any open subset of x and showed that its preimage has to be open. Okay. Well, to finish off, we can just say that the argument for p sub y is analogous. Just change things around a little bit. Same ideas. All right, part B. So the theme of this exercise is that the product topology is special, right? Not only does x times y with the product topology have continuous projection functions, okay, but it's actually the coarsest topology on x times y for which both functions p sub x and p sub y are continuous. In other words, if T is the product topology on x times y and T prime is any topology on x times y such that the two projection functions are continuous, then the product topology is contained in T prime. Okay, it's the smallest possible topology for which both these functions are continuous. Okay, well, I have a picture here. You'll understand what it means in a moment. Okay, well, technically we should show that every open set in this topology is contained in this one, but as you know, it's enough to do that for base elements. So say it suffices to show that the basis elements of the product topology T are open in the T prime topology. Okay, good. So let's consider basis element U times V of topology T with U open in X and V open in Y. Okay. Well, we know that projection functions are continuous, so let's use the first one. So since P sub X, which maps from X times Y to X, is continuous with respect to the topology T prime, we know that the preimage of this open set U, let me borrow that from up here, the preimage of the open set U, which is U times Y, is open in T prime. Right. That's by the definition of continuity. I had an open set U in X. I know that this is continuous with respect to this topology, therefore its preimage is open in T prime. Okay. Remember that this is not necessarily the product topology that I'm dealing with, so just using the definition of continuity there. All right, now same thing for P sub Y, right? Since P sub Y, which goes from X times Y to Y, is continuous with respect to the topology T prime. I have, well, what's its preimage? P sub Y inverse V, which by definition is a set of all xy in X times Y, such that Y is in V, and that's just X times V. Right, that preimage must also be open in the topology T prime. All right, well, what I really want to show is that U times V is open in T prime. Okay, but that's just the intersection of these two sets that I just proved are open. So we'll be done. It follows that U times Y intersect X times V, which is equal to U times V, is also open in this topology T prime. Okay, so any base element of T is open in T prime, therefore T is contained in T prime. Well, just to convince you of this equality down here, you can write it out in terms of the elements, but it's easy to see in terms of the picture. So here U is an open subset of X, V is an open subset of Y, and this vertical strip is U times Y, this horizontal strip is X times V, and if you intersect those two, you just get this rectangle in the middle here, which is U times V. Okay.